Jump Game 8, same length nums and costs, you start at index 0. Jumps to the right follow two strict shape rules on nums, each time you land on J you pay costs, J. Minimize total cost to reach the last index. Example 1, one cheapest route jumps from index 0 to index 2, paying 6, then from 2 to 4, paying 2. 8 total. The arrows follow the nums row because jumps are between indices. Example 2, you cannot jump straight from 0 to 2 when nums is 0 1 2, so you pay 1 to land on 1 and 1 more to land on 2. Picture nums as pillars. You stand on one bar and look only to the right. There are two kinds of first landing. Up path, the first bar whose height is greater than or equal to yours. Down path, the first bar that is strictly shorter. You are not scanning every gap in a window, you are searching for the very first index that satisfies one of those two tests. Heights 10, 15, 20. From 10, both 15 and 20 are at least as tall as you, but the up rule asks for the first index you meet when you walk right. That is 15. 20 is hidden behind that wall along the scan, so it is not a second up hop from the same start. Same idea as monotone stacks, you stop at the first boundary you hit. Imagine a beam sliding along the tops. For the up rule, skip until the first bar at least as tall as you, here that is 6. For the down rule, slide again from the same start and stop at the first shorter bar, here that is 1. If we pre-compute those two next indices for every position with monotone stacks, the jump graph is already drawn. Then shortest cost dp only relaxes a couple of edges per index. We assume you already know how a monotone stack finds things like next greater or next smaller on one pass. We will use that machinery twice without reteaching it. Before we touch costs, we need the sparse jump map. Two right two left monotone stack passes fill that in. Pass 1 records, for every index, the first position to its right whose value is greater than or equal to its own. Pass 2 records the first strictly smaller value to the right. Those are the only first hop gatekeepers we ever need, at most 2 arrows leave each index. We start at index 0 with cost 0. Every other DP cell begins at infinity until a real path reaches it. The price array costs tells you what you pay when you first land on an index. The goal is to push the minimum total forward all the way to the last index. Stand at index 0. Its green edge is the next greater or equal landing, its blue edge is the next smaller landing. Try both. Add the destination landing fee to your running cost, and write the better value into DP at that index. If a cheaper route appears later when some other index fires the same edge, DP keeps the minimum. Because every drawn edge points to the right, a single forward scan is enough. At each index you already know your best cost so far, you fire at most 2 relaxations ahead. Later indices may improve the same DP cell, and that is fine. We always keep the smaller total. When the scan finishes, the last cell of DP holds the cheapest total. Here the optimal play jumps along the example edges 0 to 2 and 2 to 4. Overall work is linear, 2 monotone passes to draw the sparse graph plus 1 forward dynamic programming pass. Let n be the length of nums. Each index has at most 2 outgoing jumps in the graph we build. Time is linear in n, 2 reverse scans with monotone stacks, where each index is pushed and popped a constant number of times on average, plus 1 forward pass that relaxes only those sparse edges. Space is linear for the adjacency lists, the DP table, and the temporary stacks, each holding at most n indices. Pseudocode for Jump Game 8. Function minCost takes nums and costs. Let n be the length of nums. Allocate G as n empty adjacency lists. Start an empty stack for the first backward pass. Loop I from n-1 down to 0. While the stack is non-empty and the top index has a smaller value than nums at I, pop. Pop from the stack. If the stack still has an index, that top is the first position to the right with value at least nums at I. Record that index in G at I. Push I onto the stack. Clear the stack for the second pass. Again loop I from n-1 down to 0. While the stack is non-empty and the top value is greater than or equal to nums at I, pop. Pop from the stack. If the stack is non-empty, the top is the first strictly smaller value to the right. Add that index to G at I. Push I onto the stack. Build DP array F of length n, filled with infinity. The start costs 0. Scan I from 0 to n-1. For every outgoing edge from I to j in G at I, relax the cost to reach j. Keep the minimum of the old f at j and f at I plus the landing cost at j. Return f at the last index.